Okay, so this problem is a little interesting. We're going to launch a projectile, some angle theta, some initial speed v naught, flies through the air. When it hits the ground at its range point, it loses all of its vertical velocity. So the coefficient of restitution for this object would be 0, but it doesn't lose its horizontal velocity. And so at this point, even though it's not going to bounce back up again, it'll slide along the ground. There's some friction with the ground, and we'll imagine that it slides along the ground until it comes to rest at some final distance I'll call capital D, which is the range of the projectile motion plus the amount of sliding along the ground, which I'll call lowercase d. And the question we want to answer is, what should our launch angle be to maximize this overall distance that it travels, the range plus this sliding distance? And you might think, okay, it's probably going to be whatever maximizes the range. Well, maybe, but again, we do want there to be some leftover horizontal velocity so that as it slides along, it still covers a great distance there. So maybe it's not as easy as just having the maximal projectile range. Okay, so first off, let's try to figure out what some of these are. And what I want to look at is, what's the relationship between the velocity immediately after hitting the ground and the velocity immediately before hitting the ground? And the tricky part here is that we should not assume that the horizontal velocity is just whatever it was immediately before hitting the ground. We know there's no acceleration during the flight. We're assuming no drag or anything like that. But the impact with the ground is going to deliver a horizontal impulse to the left because of the friction with the ground. And then, of course, it'll maintain that impulse as it slides along. So we're going to have to calculate what that new velocity component in the x direction is. And to do that, I'm going to invoke the impulse momentum theorem. So this tells us that the change in the object's momentum is going to be some time integral of the force, or net force, I should say, that acts on the object during the collision. So we're imagining this collision happens in a very brief moment of time. I'll call it like a delta t. And during that time, the net force on it will be composed of a couple different pieces. There'll be a normal force from the ground pushing up. There will be a frictional force to the left, which will be proportional to that normal force. There's also technically still a gravitational force during the collision, but we'll imagine that the impact with the ground will deliver a much larger normal force than mg, so that can be safely neglected. So in our two different directions, we'll have something like this in the horizontal direction. So the mass times change in the x component of the velocity, there'll be a negative sign because friction will be acting to the left, and then I'll use a lowercase f to stand for the frictional force over this time of collision, whatever it is. And in the vertical direction, it's the normal force that'll be contributing to the impulse vertically. Technically, you could write this as n minus little mg, but again, we're going to assume that over this time of the duration of the collision, the gravitational force is negligible compared to the normal force. Now notice, we can pull out the coefficient of, well, static friction, I guess, if it's just that instance of collision, and write this as an integral over the normal force. So even though we don't know what the normal force is as a function of time, and indeed it does change from 0 up to some max back down to 0 in some probably complicated way depending on the elasticity of the object, all I really care about is the quotient of these. And that normal force impulse will be canceled out. We can also simplify this a little bit because we know that my velocity immediately after the collision in the x direction, which I'll call Vx prime, is, well, it's kind of what we're looking for. But my velocity immediately before the collision is going to be the initial x velocity of my projectile, because again, there's no forces acting on it during its time through the air. So that's kind of nice. Similarly, in the y direction, we know that the final velocity after collision in the y direction is 0. That's the whole idea, that it's lost all of its vertical component of velocity, so it's not going to bounce back up at all. And then its initial velocity in the y direction right before the collision is actually negative its starting velocity when it was launched. So we get a little double negative thing going on here because the velocity direction is down, but it's also the initial in a delta, so those cancel out. So let's go ahead now and divide, let's see, this equation by this equation. On the left-hand side, you'll see the masses cancel out. And we're left with just positive V naught sine theta. And on the right-hand side, the normal force impulse cancels out. And we're just left with minus the coefficient of friction. All right, let's go ahead and solve this for Vx prime just by multiplying over and moving some stuff around. We'll bring that up to the top, and then we'll start using a little bit of maybe energy considerations to see how far does it slide before stopping. Okay, so there's the velocity of my projectile immediately after it hits the ground and is now moving to the right, about to slide to a stop. To find out how far it goes, we'll just invoke the work energy theorem. It's probably easiest. So we know that the work done on the projectile as it slides along this distance will be the change in its kinetic energy. There's no change in potential energy here anyway. And both sides of this are pretty easy to write down. The frictional force will be a constant, so I can just write that as F times D. This is the total distance. The minus sign is picked up because the displacement is actually opposite the direction of the force, so we have a cosine of 180 in that dot product. On the right-hand side, we know that I want to know how far it goes until it stops. So the final kinetic energy, of course, will be 0. And the initial kinetic energy, meaning right after it hit the ground, will be 1/2 times this mvx prime, this component of my velocity in the x direction immediately after the collision, squared. Remembering that after the collision, F is proportional to the normal force through the coefficient of friction, and the normal force will just equal the weight mg, because now we're not bouncing anymore. The net impulse is 0 in the vertical direction. We can do a little simplification, cancel the negative signs. I'll write this as mu mgd, and this side will just be 1/2 m, and then this whole thing squared. Okay, thankfully the masses cancel out, because we weren't really told much about the mass, and we can solve immediately for d. I'm going to go ahead and put the v naught squared over 2g out front, because that's the piece that will look similar to what we get for our range formula from the projectile piece. And I won't bother to square out that binomial just yet. All right, now for our total distance, total range, if you want to call that, I need to add back in the range of my projectile. Now, we've done this numerous times before, so I'll just remind you that the range of a projectile is v naught squared over g times sine of twice the launch angle, so sine 2 theta. So let's go ahead and write down our total distance. The v naught squared over g I'll pull out from both terms just to have a common factor. I have a sine 2 theta from the range formula. And then I have this piece that involves the coefficient of friction from my energy considerations. Okay, so that's the total distance as a function of theta. It is a little complicated. Now we have to maximize it. So let's bring that to the top, and we'll take our derivative. Okay, so there's our result. I think I had a slight typo in the last board. Forgot that factor of 1/2 compared to the no 1/2 out front here. And now we're ready to take our derivative and set it to 0 to maximize. All right, so let's go ahead and do it. We'll use the chain rule on this part. And then multiply by the derivative of the inside. Okay, let's see what we can clean up here. So this 2 and this 2 cancel. let's go ahead and FOIL out this bit. I can divide over the v naught squared over g. And let's see what happens here. I've got a 1 over mu. I'm going to go ahead and factor out a minus sign from this last term. And then we have cosine times sine. We have a cosine times a mu cosine. Remember, that's positive now. We'll have a negative mu sine times a positive sine. And we'll have negative mu times a positive mu cosine. Okay, now to collect more terms together, notice that I have a cosine squared minus sine squared attached to this mu. That's just cosine theta, cosine 2 theta. That's our double angle identity. And I'll go ahead and group these two together by invoking another double angle identity for sine. So I'll have 1/2 of sine 2 theta. And now we see something kind of nice happening. I can cancel out the mu here with the mu there. And I'll have a 2 cosine 2 theta minus 1 cosine 2 theta. That's awfully nice. And then what's left will be, let's see, a 1 minus mu squared over 2 mu sine 2 theta. And because these are both in double angle form, it's real easy to then go solve for theta, which will give us tangent to theta. And we should be careful about the ordering here. So moving it over, I should then divide this over before dividing by the cosine. So our final angle for the maximal range, or maximal total distance, maybe I'll call that theta star, will be 1/2 the arctangent of this quotient of coefficients of friction. All right, so this is kind of an interesting result. We can see that, for example, if there's no friction, if mu equals 0, then we just get theta equals 0. And effectively, that just means fire it straight. It's just going to slide forever anyway. It's not going to matter one way or the other. You'll actually get infinite range no matter what. We could also figure out a specific value. If we were to choose, say, mu equals 1/2 or something, we could go find what that angle is. We could also note that there's something interesting that happens when mu equals 1. So if we happen to have a very strong friction so that the frictional force and normal force happen to kind of cancel each other out, then I'm dividing by 0 here, and the arctangent of that is effectively pi over 2, which means I recover that original pi over 4 maximal launch angle. In other words, what will happen there is when it lands, that initial impulse will stop it dead in its tracks. So I'm not talking about the sliding part afterwards. There won't be any sliding part if it actually stops completely before it begins to slide. And in that case, we should see just the usual range, which is maximized by a 45-degree launch angle. So there it is. That's our angle, assuming that the projectile loses all of its vertical component of velocity upon hitting. Now, you could redo this problem where we do not go through that initial bit looking at the impulse delivered by the initial collision, and you can just sort of pretend that the horizontal component of velocity is maintained through the collision. It's not quite as correct. And maybe try that one out and see. It makes the math a lot easier, but what happens to the maximal range in that case? So our result is given. And if you want, you can now go plug this back in to our value for D and find out what that maximal range is in terms of V naught squared over G. QED.